Okay, this is acid-base theories, and this is the first video in our acid and base chapter. So in class we talked about properties and how to name acids and bases, and so now this is going to talk about some of the major theories behind what makes an acid and what makes a base a base. Okay, the first thing that kind of launch us into this is to remember that acids and bases are held with ionic bonds. Okay, so that means that when they're added to water, they are going to ionize and split into their different components. And so if you add, for instance, hydrochloric acid, HCl, into a beaker of water, they're going to ionize into H plus ions and Cl minus ions, just like a normal ionic bond, okay? And that's called ionization. It's also, you might hear it called dissociation, because they're, instead of associating with each other, they are dissociating with each other and splitting, okay? So ionic bonds in a lot of acids are going to ionize when they hit water and make more ions, okay? So first we're going to talk about strong acids and weak acids, and strong bases and weak bases. So what makes a strong acid, or a strong base is not how much it burns you. That is not a very good measure, because then that means somebody would have to sit there and pour it on their hand to figure out all these acids and whether they're strong or not. So what we use is basically how well it conducts electricity. And so if an acid is strong or a base is strong, that means it's going to be a strong electrolyte, which means two things. If it's a strong electrolyte, we can test that by how well it conducts electricity. We can hook up a light bulb and a battery and see how bright the light bulb is, and that will tell us how well it conducts electricity. And then two, that means that it ionizes completely. So all the bonds will split. So for acids, that means we will have a very high concentration of hydrogen ions. And for bases, we will have very high hydroxide concentrations. So a lot of H plus for acid and a lot of OH minus for bases. Okay. For a weak acid or a base is one that is a weak electrolyte, which means if we hook it up to a light bulb, it's going to be very dim and it will conduct electricity poorly, and it will ionize incompletely, so not very well. We won't have very much H+. So here's an example. Here are two beakers, one with hydrochloric acid and one with hydrofluoric acid. They both have the same concentrations of 0.1 molar, but if you notice, in the hydrochloric acid, every single ion is split. There's no HCl that's still together. But if you look on the HF side, hydrofluoric acid, some of them are still HFs, while some of them split off into HF and F minus. So this is a strong acid because all of them are ionized, completely ionized, so it's going to conduct electricity very well. Whereas on this side, you still have HF together, partially ionized, and so it will not conduct electricity very well. So this is a strong acid, and this is a weak acid. So here's some examples. Examples of strong acids would be hydrochloric, sulfuric, and nitric acids. Some examples of weak acids would be acetic acid. That's like vinegar, right? Acetic acid. Hydrofluoric, like we just saw, and nitrous acid. Okay, some examples of strong bases are sodium hydroxide and potassium hydroxide. They will ionize very well. And some example of weak bases are ammonia and then ammonium hydroxide. Okay. So the next thing to talk about is the hydronium ion. Okay. In real life, there is no such thing as H+. Okay. So when we look through the molecular structures, we actually find that there is no such thing as a lone H+. Instead, when an acid ionizes, those H+ ions will pretty much immediately bond to a water molecule, H2O. And so what we find are actually hydronium ions, which are H3O+. So it's a water molecule with an extra H+ on it, and so it's H3O+. And so technically they're different, But at this level, they're pretty much the same thing. But you need to know that if you see H3O+, they're really talking about a hydrogen ion. So we will use hydrogen ions, H+, kind of as a shortcut, but it's really the same thing. So here's an example, and pardon the blurriness, but I wanted it big enough so you could see. So when you add HCl into a beaker of water, it ionizes completely, right? H plus and Cl minus. But in reality, instead of H plus, we're really talking about hydronium, so H3O plus and then Cl minus is floating around. And then this is the pictorial model version. And so here's an HCl molecule, and when you add it, that H bonds on to other water molecules, so you get H3O pluses and then the Cl minuses. Okay, so now we're actually going to talk about the three main theories for acids and bases. The first one was by a guy named Arrhenius. And Arrhenius said that all acids are ones that donate H plus, that donate hydrogen, okay, or create H3O plus in reality, right? And then all bases are ones that contain hydroxide and donate and give away hydroxide when you dissolve them. So for example, all the some Arrhenius acids are what we've been talking about so far. So all the acids and bases that you know right now are Arrhenius acids. Remember when we said that all acids start with H? That's an Arrhenius rule, because he said all acids have hydrogen and give away and donate hydrogen, and all bases have hydroxide and give away hydroxides. Okay? So for Arrhenius, all acids are going to have hydrogen and all bases will have hydroxide. So what you know so far is just the Arrhenius acid-base theory. So then eventually people discovered other chemicals that didn't have hydroxide and didn't have hydrogen, at least, that were still acids and bases. They still had pH if we can test it with a litmus paper, and they still are giving us a pH even though they don't have hydroxides in them. So these guys were named Bronsted and Lowry, and they kind of came up with this theory at the same time, so we give credit to both of them. So Bronsted and Lowry said that an acid is actually one that just donates a proton to a solution, and a base is anything that will accept a proton. So an example is HCl, H2SO4, and then now we have NH4+, because NH4+ will donate a proton to a solution, okay? And then bases are now NH3 and OH-, okay? So a Bronsted-Lowry base, NaOH does not qualify, because NaOH will not accept a proton. But when you dissolve NaOH, it's going to break off into Na plus and OH-, and OH- can accept a proton. Okay? So you might be like, how on earth is it going to accept a proton, and how does anybody know that it accepts the proton or donates a proton? Well, if we think about it, really a proton is just a H plus molecule, right? Hydrogen normally is a proton in the center, right? One proton with one electron on the outside. So if you remove that electron and becomes H plus, the only thing you are left with is this sole proton in the center. So that's why a proton really is just a hydrogen ion. Okay, and really in real life, remember that hydrogen ion or that proton is going to bond with H2O, and that becomes H3O plus. But we use hydrogen ion as kind of a shortcut. So when we say in Bronsted-Lowry that acids are proton donors, we really mean that they're H plus donors, and bases accept H plus. But they officially said protons, so you need to be able to make that connection. Okay, so the third acid-base theory is from Lewis, and the same guy that made Lewis electron structures, remember with the Lewis diagrams, dot diagrams that you had to do? He also said, well, really an acid is anything that accepts an electron pair, which is kind of like the opposite of saying donates a proton would be accepting an electron, and that's how they donate the proton, is because they accept an electron pair in place of it. Okay, and then that means a base is going to be anything that donates an electron pairs. So he's pretty much saying, it's kind of like saying the opposite of the Bronsted-Lowry theory. But what that meant is that it is the most broad definition. So Arrhenius had a very small range, only H plus and OH. Then Bronsted-Lowry say, okay, anything that accepts H plus is going to be a base, and anything that donates H is an acid. And then Lewis was like, no. Everything that accepts electrons is an acid, and anything that donates electrons is a base. And so Lewis contains all Bronsted, Lowry, and Arrhenius acids. And so Lewis, under the Lewis definition, a lot of things are considered acids and a lot of things are considered bases. And then on Monday, we're going to talk about identifying a Bronsted-Lowry acid and then identifying an Arrhenius acid and stuff like that. So here is a chart that kind of concisely restates everything we just said. Okay, there's three theories: Arrhenius, Bronsted-Lowry, and Lewis. Arrhenius theory: acids are hydrogen ion donors, and then bases are hydroxide donors. Under Bronsted-Lowry, acids are proton donors, and bases are proton acceptors. Right? And remember, hydrogen and protons are the same thing. So they're both donate, except instead of donating OH, they accept OH, or accept protons. But that's really the same thing, because an OH minus is a proton acceptor. And then Lewis came along and said, all of these are true, but anything that accepts an electron pair is going to be an acid, and anything that donates an electron pair is a base. Okay? So those are the three theories. And then on Monday, we're going to actually talk about like applying that and then looking at a formula and picking out, is this an Arrhenius acid or is this a Bronsted-Lowry acid? Okay, so again, another small thing is that there are different types of acids. So we said that they give away protons or they give away hydrogen ions, right? So if an acid is monoprotic, mono means one and protic means proton. So if an acid is monoprotic, it will give away one proton. So an acid that donates one proton or one hydrogen ion is monoprotic. So for example, HCl and HNO3 only have one hydrogen to give away in both cases. Okay? So again, let's say it's diprotic. Di means two and protic means proton. So an acid that donates two protons. So like H2SO4 is going to be able to give away two protons or two H plus molecules. If an acid is triprotic, then guess what? It's going to give away three protons. So example would be H3PO4, okay, because it has three hydrogen ions to give away. Okay, so here's some practice. So pause the video, write down these 5 acids, and then I want you to tell me whether it is mono, di, or triprotic. So pause the video and do that. Okay, so here's the answers. Okay, H2S has 2 hydrogens, so it is a diprotic acid. HClO3 is monoprotic because it only has 1 hydrogen. HF is monoprotic, 1 hydrogen. H3P is triprotic because it has 3 hydrogens. And then acetic acid, HC2H3O2, is monoprotic because it has 1 hydrogen ion to give away. Don't be confused that there is an H3 here. Remember, acetate, H2C3O2, is going to stay together and it will not break up. So that does not count as an hydrogen ion because it will stay all together. It only will give away 1 hydrogen ion, so it's monoprotic. Okay, so the last thing we are going to talk about is neutralization reactions. So remember that we said that when you mix an acid and base together, they will neutralize each other and it makes salt and water. A salt, not NaCl, not table salt, but just A salt. So for example, If you wanted to make table salt as your salt, you would mix hydrochloric acid and sodium hydroxide because it will make water and NaCl. Okay, so what kind of reaction is taking place? Remember, you have different reaction types. You have single replacement, double replacement, redox, and combustion, decomposition, and synthesis. So of those, this is going to be a double replacement reaction because you are doubly replacing. H and OH is going to replace, and then Na and Cl are going to replace because H and OH together make water, and they will cancel out and neutralize into water. Whereas Cl and Na then combine and make NaCl. So it's a double replacement because two swaps occur. So again, here's kind of looking at it on the ion level. H and Cl are going to ionize into H and Cl plus and minus. Na and OH are going to ionize too, right? So those H plus, this H plus, and this OH minus combine to make water. Oh, don't go next. Combine to make water. H plus and OH, because that's the same thing as H2 and O, and that plus and that minus combine together. And then you have Na and Cl over here, and then they're going to combine over here to make Na plus and Cl minus. And so that's where you get the water and the salt, because the ions can combine. So that's double replacement. You are replacing both sides. And so an acid and base makes water and salt. So I want you again, pause the video and write down these reactions, and I want you to practice, and you need to be able to predict what is going to happen on the other side. Remember, you're making water and a salt. So pick, and you have to be able to identify what part is going to make the water and what part is going to come together to make the salt. Okay? So pause the video, write this down, and I want you to practice and try to predict what's going to happen, and then I'll tell you. So here is what's going to happen. Okay? HNO3, nitric acid, and potassium hydroxide. Well, you know it's going to make water and a salt, right? So after you cancel out the H and the OH, right, that's going to make the water. And so you're going to be left with K and NO3. And so K and NO3 combine to make potassium nitrate over here. So that's how you know how to make your salt. Okay? And remember, you're going to use the crisscross rule, but K is just plus 1 and NO3 is just minus. And so when you crisscross, you get 1 and 1, so that's why we just keep it as KNO3. So let's look at number 2. Okay? The OH and the H are going to make water, right? And so that means my salt is going to be made of Ca, calcium, and sulfate. Okay? Ca is plus 2, and sulfate is minus 2. So when you crisscross plus 2 and minus 2, they're going to cancel because they're both 2's, and so you just get water and then CaSO4, calcium sulfate. Okay? Then lastly, number 3. Again, the OH and the H are going to combine to make water, so we can cancel those out. And then we have Mg left, and then we have PO4 phosphate left. Okay? PO4, oops, I'm about to die, is -3, and Mg is plus 2. So that means when you crisscross it, the 2 is going to come down here, and the 3 is going to go all the way over here to Mg. Okay, so that means I'm going to have water and then magnesium phosphate, which is going to be Mg3 PO4 2. Okay, so look over this, make sure you understand it. If you don't, come ask me, because this is going to be a part of your quiz, and this is what we're going to practice on, because we need to be able to predict an acid-base neutralization and know what's going to happen when we mix an acid and a base together. Okay, so here's a mastery check. And so I'm kind of giving you this ahead of time. So check yourself to see if you learned what you needed to learn from this video. So pause the video and see what you got, and then press play. Okay, so here's what you're going to do. On number 1, when you combine it, and if you have the correctly lithium or correctly balanced, really this question is even just asking which one is correctly balanced, okay? And then the correctly balanced one is going to be, drum roll, it's going to have to be A, okay? Nope, not A. Wait, no, I forgot. This is embarrassing. Okay, it's going to be B, okay? Sorry, I thought A, and then I was like, wait, that 2 shouldn't be there. Okay, B is the only one that balances correctly with H2 and H2, SO4, SO4, 1 lithium, 1 OH, and 1 OH, okay? So, B, and then number 2, consider the chemical equation. In this reaction, why is H2S considered an acid? Well, even though H2S starts with hydrogen units, an acid, it is giving away its protons to this OH. And so it would be B, H2S donates a proton. A, C, and D are all characteristics of bases anyway, so they don't even make sense. So again, 2 is B. So that is the end of this video. Remember, you have a video quiz and a note check. Sorry that the video went on for 21 minutes, but it will get us nice and set up to practice this on Monday.